Hi everyone, I am Dr. Harikrishna Mulam, Associate Professor, Department of EIE. In this lecture, we will see how to solve one more problem related to time response analysis. The problem is a closed loop servo is represented by the differential equation d square c by dt square plus 8 dc by dt is equal to 64e. So, the differential equation governing the system, is d square c by dt square plus 8 dc by dt is equal to 64e. Okay, and where C is the displacement of the output shaft. Whatever C that is we are mentioning here, it is the output of the system. C is the output of the system, displacement of the output shaft. So overall it is output. Then R is the displacement of the input shaft. That is, you can consider R as the input. Okay, R as the input. And E is the error present in the system. Error present in the system is the difference between input and output. Input actually corresponds to the desired output and output is the actual output. The desired output and the actual output, the difference between them is called as error. So here whatever we have written, E is the error present in the system, which is the difference between input R and output C. Therefore, this differential equation governing the system can be written as d square C by dt square plus 8 dc by dt is equal to 64 into this error can be written as difference between input and output, that is E can be written as R minus C. That is equal to 64R minus 64C. And you can send this minus 64C to the left hand side so that it becomes d square C by dt square plus 8 dc by dt plus 64c is equal to 64r. Though here we have written only C, R like that, actually speaking they are C of t. You should write it as C of t, output in time domain, R of t, input in time domain, in that manner. For simplification, we are omitting that of t. Okay, so now this differential equation is purely in terms of output and input. Okay, and here you are asked to find undamped natural frequency of the system omega n, damping ratio of the system zeta, and percentage maximum overshoot of the system, which is represented as percentage m suffix p, which is one of the time domain specifications of the system when the input is a unit step input. That is input R of t is unit step input, that is R of t is equal to 1. R of t is equal to 1. Now, in order to find this undamped natural frequency or damping ratio, first of all you need to get the closed loop transfer function of the system. Okay, and in order to get the closed loop transfer function of the system, okay, the closed loop transfer function of the system is defined as ratio of Laplace transform of output to that of Laplace transform of input. Therefore, you can get this expression by taking the Laplace transform of this entire equation. Now, we need to know few formulas. What is the Laplace transform of d square c by dt square? The general formula is Laplace transform of d square some variable x by dt square can be written as s square into x of s. Okay, this is the equation that is valid under zero initial conditions because the transfer function is defined under zero initial conditions. Similarly, the Laplace transform of dx by dt is given by s into x of s under zero initial conditions where this closed loop transfer function is defined. Similarly, Laplace transform of x of t is equal to capital X of s. These are the formulas that are required to get the Laplace transform of this differential equation. Therefore, Laplace transform of d square c by dt square can be written as s square c of s plus Laplace transform of 8 dc by dt is 8 into dc by dt Laplace transform is s into c of s plus 64 is the constant. Laplace transform of c is c of s is equal to 64 into Laplace transform of r of t is r of s. Therefore, if you take c of s common on the left hand side, okay, remaining terms are s square plus 8s plus 64 into c of s is equal to 64 r of s. Therefore, this c of s, bring this r of s to the left hand side so that it becomes c of s by r of s is equal to 64 by this term will go to the denominator on the right hand side, s square plus 8s plus 64. This is the closed loop transfer function of this system. The closed loop transfer function of this system. And if you want to find this omega n and zeta, you need to compare this transfer function with the standard way of representing closed loop transfer function of second order system, that is omega n square by s square plus 2 zeta omega ns plus omega n square. So if you compare these two expressions, the denominator of the actual transfer function with the denominator of the standard transfer function, then you can write omega n square is equal to 64. Therefore, omega n is equal to square root of 64, which is equal to 8 radians per second. Okay. Then this 8s is equal to 2 zeta omega ns. Therefore, 2 zeta omega n is equal to 8. Therefore, zeta is equal to 8 by 2 omega n. That is 8 by 2 into omega n is 8 radians per second. 8 gets cancelled, 1 by 2, which is 0.5. Zeta is equal to 0.5. We know that if zeta is equal to 0, it is undamped system. Zeta is equal to 1, it is critically damped system. Zeta is greater than 1, it is overdamped system. But if zeta value, if it is in between 0 and 1, 0 less than zeta and zeta less than 1, such a system is called as underdamped system. Underdamped system. As zeta is in between 0 and 1, the system is called as underdamped system. So we have found omega n, we have found zeta, and now we need to find percentage overshoot. And we know that we have mainly 4 time domain specifications. One is rise time, the second one is peak time, next one is settling time, and one more term is percentage overshoot. These 4 are called as time domain specifications. Okay, all these time domain specifications can be calculated if you know the omega n value and zeta value. Okay, if you know these two values, you can find all these time domain specification by using the formula. But in this problem, we are asked to find only percentage overshoot. So percentage overshoot is given by the formula e power minus pi zeta divided by square root of 1 minus zeta square into 100. This is the formula for percentage overshoot. That is equal to e power minus pi, zeta is 0.5 divided by square root of 1 minus 0.5 whole square into 100. If you find its value, it will come around 16.3%. So the percentage overshoot in this system is 16.3%, which gives you information about to what extent the overshoot has been extended beyond the desired output. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.